Where we are. So chemistry 1411. Today is January 29th. So today we are doing review, and then exam one will be on Monday. There is no lecture on exam day, and so you have the entire day to do the exam. If you want to go to the university to write it at the library, I would say it's a good idea. If you're unfamiliar with Respondus, remember that I've also set up a practice exam that requires Respondus. And so I highly encourage you to write that practice exam online so that you get some practice, with Respondus. So the equation sheet for the first exam looks like this. Okay, I'll make 100% sure to update the equation sheet link for the quizzes, or sorry, for the exam, so everything will be good. But this, hear ye, everybody who's hearing the sound of my voice, this is the equation sheet you will have for exam one, okay? Not the old one. I tried to make it as simple as possible. You can see that I didn't tell you what the integrated rate laws were, but if you can count from 0 to 1 to 2, you would know that these are 0, first, and second order respectively. I just literally copied and pasted all of these formulas directly from the OpenStax textbook onto this slide. So everything that you need is on here, okay? All the formulas anyway. Cool? Capiche, capiche? Give me a thumbs up if you're like, I like the equation sheet. I will be using it during the exam. Okay? All right, good. There we go. Well, let's get back into the practice exam. In last class, we ended off around question 10, somewhere thereabouts. And so that's where we're going to start off today. And again, as I told you last class, if we end up getting through all of the practice exam today, and there's a good chance we will take the rest of the class. And there's a couple of problems in the notes that we didn't do that I would like to go take a look at. Again, I also posted the solutions to those to Canvas. So everything you need, or everything that I can give you, is posted. But anyhow, I digress. Let's start by looking at question number 10. Deals with second order rate laws. It says here, a certain reaction, A, giving you products, is second order with respect to A, with a rate constant of K being equal to 0.122 molar to the minus 1, minutes to the minus 1, starting with an initial concentration of A, which is 1.01 molar. How many seconds will it take for A to reach a concentration of 0.750 molar? So this is a second order reaction. It tells us that right here. And there we go, second order. And so we could write a rate law for this. We could say that since our reaction is A is giving us our product, we could say that the rate is equal to K times the concentration of A squared. Again, since it's second order, we know that our rate constant K is equal to 0.122 molar to the minus 1, minutes to the minus 1. And we are given an initial concentration of A as being 1.01 molar. We're given a concentration of A after an amount of time, T, being equal to 0.750 molar. And we're asked to determine what is T. Okay, that's what we're trying to figure out. How much time is it going to take? And you can see that they've given us the time in seconds. Okay, but they've given us our rate constant in a molar to the minus 1, minutes to the minus 1. The reason I'm pausing is because I'm looking at my solution that I worked out on my own spare time, and I might have made a mistake here. But anyhow, let's get into it. We have the second order integrated rate law. So if we do second order integrated rate law, okay, it looks like this. 1 over A subtract 1 over the initial concentration of A is equal to KT. We want to solve for T. If we rearrange the formula, we get that T is equal to 1 over the concentration of A minus 1 over the initial concentration of A divided by K, like that. So now it's just a matter of plugging in our numbers. All right. And let me just double check something before I keep going. Okay, so let's keep going on, and let's plug in some numbers. So we have 1 over concentration after our amount of time, which is 1 over 0.750 molar. Subtract 1 over 1.01 molar. All right, and then we're going to divide that by our K, which is 0.122 molar to the minus 1 minutes to the minus 1. I'm just going to double check my calculation here. I might have made a mistake in my solutions. 0.750 subtract 1 divided by 1.01 divided by 0.122. Okay, looks good. All right, so we see that molar to the minus 1 is going to cancel out, and we're left over with minutes to the minus 1 in the denominator. And so that means that our answer will be in minutes, and we get 2.81 minutes. Now you see that all of the answers are given in seconds. And if I want to convert 2.81 minutes, well, I know that in 1 minute, I have 60 seconds. So minutes will cancel out. If I take 2.81 and I multiply it by 60, so 2.81 times 60, I end up with 169 seconds. And so the answer will be B, 169 seconds. And while you're looking at question 11, I'm just going to make a quick correction here in my solutions. I made a little mistake here. All right, well, let's move on to question number 11. It says, the reaction of 2NO2 producing 2NO plus O2 is suspected to be second order in NO2. So suspected to be second order. So that means our rate law would look like this. Rate is equal to K times NO2 to the power of 2 because it's second order. Then it says, which of the following kinetic plots would be the most useful to confirm whether or not the reaction is second order? I'm going to throw that out there to my students. Can anybody answer this one? If it's second order, what would be the plot that you would want to look at? It's not A, no. Okay, great. No, yes, sorry. I see some people saying that it's E, and that is correct, right? It must be E. And the reason why is because if the reaction is second order, if we go back to the integrated rate law for a second order reaction, we saw that the form of y equals mx plus y is equal to mx plus b is y over the concentration, or 1 over the concentration of A is equal to kt plus 1 over the initial concentration of A, like that. That is in the form y is equal to mx plus b, like that. So that tells us that we are going to get a linear plot if we plot 1 over the concentration of A versus time, right? Then we end up with a slope that is equal to K, and we end up with a y-intercept that is 1 over the initial concentration of A. And so we're going to graph y versus x. Our y is 1 over A, and our x is t. And so the answer is the reciprocal of the concentration of NO2, NO2 to the minus 1, right? Because NO2 concentration to the power of minus 1 is the same thing as 1 over the concentration of NO2 versus time. And that's why we spent some time looking at integrated rate laws and how we make a linear plot. All right, let's move on from there to question 12. It says for a chemical reaction, A produces B plus C A plot of the concentration of A versus time is found to give a straight line with a negative slope. What is the order of the reaction? Could anybody tell me what the order of this reaction would be if I'm getting a linear plot from the concentration of A versus time? Exactly. It's zero order, right? We looked at this already in detail. And if you go back to our equation sheet, okay, you see that for a zero order reaction, right? This is a zero order reaction. We see the zero order integrated rate law is the concentration of A is equal to negative KT plus the initial concentration of A. That tells us, where's my pencil? That tells us that when we go back into our exam, which is way back here, okay, since we get the form y is equal to mx plus b, which again is concentration of A is equal to negative KT plus A, the initial concentration, and this is for a zero order reaction. We would have a plot of time on the x-axis, and on the y-axis we would have the concentration of A. We get a slope that's equal to negative K, and we have a y-intercept, which is equal to the initial concentration of A. And so that tells us that this is a zero order reaction. Let's try something very similar. Question number 13. This is a kind of like ACS final type question where they just show you a bunch of pictures and ask you to interpret. You know, could anybody tell me, all of these graphs here, all three of these graphs represent the same reaction, but what's the order of the reaction? And it's not a trick. This one is zero order, right? Because these two are nonlinear. These are curved. We're looking for a linear slope, right? This one is linear, and the plot is concentration of A versus time, which is zero order. The exact same thing we saw in the last one, right? We plot the concentration of A versus time in a zero order reaction, and we get a linear slope. Okay, it doesn't mean that you can't plot the ln of A and you can't plot the reciprocal of the concentration of A. However, those don't give you linear plots. All right, there we go. Let's move on to question 14. It says the activation energy for this reaction is 71 kilojoules per mole. How many times greater is the rate constant for the reaction at 170 degrees Celsius versus 150 degrees Celsius? So in order to solve this problem, we're going to need to use the Arrhenius equation, which again will be provided for you. It's ln of K1 over K2 is equal to the activation energy over R is a constant, times 1 over T2 minus 1 over T1. We're given our activation energy, which is 71 kilojoules per mole. I'm going to convert that into joules per mole because R is 8.314 joules per mole Kelvin. And now that I have that written down, I'm going to put here add R to handout. I'm going to give that to you so you don't mess that up. So I'll provide that number. So this would be equal to 71,000 joules per mole. Okay, we've got that. Then we have our T1 and our T2. Now, since I'm going to determine the ratio of K1 to K2, right? Because we're asking for how many times greater is the rate constant, one over the other, right? So I want to calculate how much greater is K1 going to be than K2. Now, I know that K1 is going to be the higher K1 or the higher K. That's the way I'm going to set it up. And the one with the higher K is going to have the higher temperature. So that tells me that, my T1 is going to be equal to 170 degrees Celsius, which is equal to 443 Kelvin. And my T2 is going to be equal to 150 degrees Celsius, which is equal to 423 Kelvin, like that. Look at what happens when I plug my numbers in. Again, I want to determine the ratio of K1 over K2, right? If I get a number of, the ln of K1 over, or sorry, if I get K1 over K2 is 2, for example, that would mean that K1 is twice as fast, okay? So what am I going to do? If I want to solve for K1 over K2, I'm going to take the anti-natural logarithm of both sides. So I rearrange the formula, and I get that K1 over K2 is equal to E to the EA over R times 1 over T2 minus T1, like that. So again, I get that K1 over K2, which is going to be my answer, is equal to E to the power of 70, what was it, 71,000 joules per mole divided by 8.314 joules per mole Kelvin times 1 over 423 Kelvin subtract 1 over 443 Kelvin. Like that, you can see that all the units are going to cancel. Joules and moles, Kelvin cancel. And when you plug that into your calculator, you end up with K1 over K2 as being equal to, it gives you a number that's like 2.488, you know, with all kinds of spinach after that. So that means that K1 over K2 is, since we only have 2 sig figs in these numbers, right? We only have 2 sig figs here. It's going to be equal to 2.5 when we round up, okay? So the best answer here would be 2.5 times faster. Remember, we talked about collision theory, and we said, well, if you crank up the temperature, you're going to have a greater number of molecules with enough kinetic energy to surpass the activation energy. So it makes sense that when you turn the temperature up from 150 and you go to 170, that the rate is going to increase. The rate is going to increase, in this case, by a factor of 2.5 times. All right, let's move on to question 15. So, question 15, it says, at 30 degrees Celsius, by how much is a reaction's activation energy decreased by the addition of a catalyst if the catalyst triples the reaction rate? Well, what I'm comparing here is I'm going to compare a catalyzed reaction and an uncatalyzed reaction, and I want to compare their Ks, right? Their rate constant. How fast is the reaction going to occur? And so the formula that I'm going to come back to over and over here is that K is equal to, a rate constant is equal to collision factor to the power of negative EA over RT, like this. And I'm going to put the whole thing in brackets like that, factor it all together. Okay? So what I'm going to do is I'm going to, again, compare KU, which is going to be the uncatalyzed reaction, and I'm going to compare it to KC, which is the catalyzed reaction. Catalyzed reaction. Okay? I'm tripling the reaction rate, so that tells me that the K catalyzed, Kc, is equal to 3 times Ku, isn't it? Right? Where did I get this from? It's telling me that when I add a catalyst, it's going to triple the reaction rate. So again, the catalyzed reaction is 3 times faster than the uncatalyzed reaction. Okay? So now I'm going to compare the now I'm going to compare the ratio of the K catalyzed versus the K uncatalyzed. Or another way of expressing that would be 3 times the uncatalyzed reaction over the uncatalyzed reaction. So that's what I'm going to compare, is these two things. All right, and then I'm going to solve for the activation energy. Let me show you how we would do that. Well, if I have this formula right here, I'm going to write an expression that relates 3Ku and Ku to this equation. Let me show you what I mean. I'm going to say that 3Ku, 3 times the uncatalyzed reaction, or the catalyzed reaction, is going to be equal to the collision frequency, or collision factor, to the power of negative EA minus X over RT. Now, you're probably wondering, what is the minus X? Well, remember that when we have our catalyzed reaction, what did it tell us? It told us that the activation energy is going to decrease. So I start with my regular activation energy and I'm going to lose an amount. And that's what these answers are, right? The answer is going to be how much does the activation energy decrease? So we're actually, in fact, solving for the amount, this X. How much is it decreasing? If you're wondering, well, how am I going to figure that out? Well, remember that we're going to compare this to the uncatalyzed reaction, which is simply equal to A times E to the negative EA over RT. So all I have to do is solve for that X. Now, is there going to be some algebra involved here? The answer is absolutely there will be. Let's start by canceling what's easiest first. You see that KU cancels. The steric factor is unimportant too. And if we cancel those two out, we end up with something that looks like this. We end up with 3. The number 3 is equal to E to the power of, is equal to E to the power of negative EA minus X over RT. And since I'm dividing two exponents, I'm going to subtract them, right? This is just algebra. So subtract the negative EA over RT like this. So it's essentially the same thing as adding it, isn't it? So I can simplify that to 3 is equal to E. And now I'm going to factor these out. Okay, so I'm just going to do some factoring here. So this is just, 10th grade math. So I have negative EA over RT minus X over RT. And then a negative, subtract a negative, gives you a positive. So plus EA over RT like that. Now look, we can see that we have negative EA over RT and positive EA over RT. Those two are going to cancel each other. So I end up with, simplifying again, 3 is equal to E to the power of negative X over RT. Now all I have to do is solve for the X. Did I put negative X when I meant to put positive X? Oh, shoot. Okay, this should have been a positive X, right? Negative times a negative gives you a positive. My mistake. Anyhow, there we go. So we have a positive X over RT. How am I going to solve that for X? Okay, all I have to do is take the logarithm of both sides, and I get that the natural logarithm of 3 is equal to X over RT. I can solve that for X. I get that X is equal to the ln of 3 times R times T. X is equal to the ln of 3 times the gas constant, which is 8.314 joules per mole Kelvin. They told me the temperature at the very beginning. Temperature is equal to 30 degrees Celsius, which is equal to 303 Kelvin. I plug that in. 303 Kelvin. Kelvin cancels out, and I end up with the amount that the activation energy is going to decrease as being equal to 2.77 times 10 to the power of 3 joules per mole. You look at the answers, some of them are given in kilojoules, so I'll convert that into kilojoules as well. We know that there are 1,000 joules in 1 kilojoule, so if we divide this number by 1,000 joules per kilojoule, we end up with X being equal to 2.77 kilojoules per mole. And that is the final answer, 2.77 kilojoules per mole. All right, there we go. So, kind of a challenging problem, a little bit of algebra here. And yeah, just comparing the catalyzed reaction with the uncatalyzed reaction and determining how much the activation energy is decreased by. Well, let's move on from there. It's, we still have some more problems to go over. Let's try question number 16. I think this one is an order of magnitude simpler maybe than the last problem, but it says calculate the activation energy in kilojoules per mole for the redox reaction shown here. So we have tin 2 plus 2 cobalt 3 plus gives you tin 4 plus and 2 cobalt 2 plus. We have two reactions, or two experiments, and we have the temperatures and we have the rate constants for both of them. Well, I'm going to go ahead and I'm going to convert these temperatures into Kelvin because temperatures in degrees Celsius don't really help us a whole lot in any of the formulas that we use. 2 plus 273 gives me 275 Kelvin, and 27 plus 273 gives me 300 Kelvin. So those are the respective temperatures, and I want to calculate the activation energy. So the formula I'm going to use will be the Arrhenius equation, ln of K1 over K2, we're given both of the Ks, is equal to EA, that's what we're looking for, over R, that's a constant, 1 over T2, we're given both of the temperatures, 1 over T2 minus 1 over T1, like that. So I have to rearrange this formula and solve for activation energy. All right, let's give it a shot. So I'm going to write that activation energy is equal to the ln of K1 over K2 divided by 1 over, 1 over T2, divided by 1 over T2 minus 1 over T1 multiplied by R, the gas constant. There we go. There's the formula that I need. Now we can just plug our numbers in. I'm going to call this one K1. Oops, where's my pen? I'll call this K1. Come on, K1, and I'll call this one K2. So this will be T1, and then this will be T2, like that. All right, and then we're just going to plug our numbers in. So let's do that. We get the EA is equal to the ln of K1 over K2, so 27.0 times 10 to the power of 3, moles to the minus, molar to the minus 1, seconds to the minus 1, divided by 3.12 times 10 to the power of 3, molar to the minus 1, seconds to the minus 1. We divide that by 1 over T2, which is 275 Kelvin, subtract 1 over 300 Kelvin, and then we take all of that. Let me get the pixel eraser here. Clean that up. We take all of that and we multiply it by 8.314 joules per mole Kelvin. Okay, and there you see that the units of reciprocal molar and reciprocal seconds cancel. Kelvin cancels, and we're left with joules per mole. And notice that all of our answers are in kilojoules per mole, so we'll have to do one conversion at the end. Anyhow, when you punch all that into your calculator, you end up with the activation energy being equal to, I got 5.92 times 10 to the 4th power joules per mole. And I'm going to convert that into kilojoules. I know there's 1,000 joules in 1 kilojoule. Okay, like that. And we end up with 59.2 kilojoules per mole. Like that is being equal to our activation energy. Like that. All right, give me a thumbs up if you feel like you could do that one. Give me 2 rate constants, 2 temperatures. All I'd have to use is the Arrhenius equation to solve for an activation energy. It's really just plugging in some numbers and knowing which formula to use. Nothing more than that.
I have a quick question.
Go for it.
So how do you know which equation to use? Like when you look at the problem, look at the what it gives you, how do you know that you should use the Arrhenius equation as opposed to another one?
Well, it's the only equation. I mean, you're probably not going to like my answer, but it's the only equation that we can use to solve this problem, right? Part of general chemistry too is being able to read the problem and interpret, which equation do I have to use? If I was to tell you, plug in the numbers in this equation, okay? If I was to just say, plug the numbers in that equation, well, everybody could solve that, right? The difficult part is being able to read it and say, how do I get from here down to the final answer, right? Multiplication, division, natural logarithms, anti-logs, if we have a computer, we can do those things. So the answer is, I don't really have a good answer for your question. The best thing to do would be to practice. And another thing you could do would be to write down what you have, okay? Write down all the information and say, what do I have? What am I solving for? And use kind of a strategy like that. If you think all the way back to general chemistry, right? If we think of something really easy, if I give you the mass of something, and if I give you the volume of something, right? And I ask you to determine the density, well, how do you know? You just have to memorize the formula D is equal to M over V. Then you substitute in X over Y, right? So it's the same kind of strategy in general chemistry 2 as it was in general chemistry 1. And, you know, that's like one of the most difficult things with the class is being able to determine which formula to use. So you have to just write down what you've got and then use your knowledge to be able to determine which formula to use. Does that help a little bit?
Yeah, it does. Thank you very much.
Okay, no problem.
I have a question.
Go ahead.
How do we decide which will be T2 or T1?
Doesn't matter. It doesn't matter at all.
Okay.
You can go back. Everybody can test me on this. You can go back and you can switch K1, K2, swap T1 and T2. You'll get the exact same answer. It doesn't matter at all.
Okay, thank you.
No problem. All right.
So K1 and K2 don't have to correspond to T1 and T2? Like if you switch one, do you have to switch the other?
Whoa. Absolutely, they have to correspond, right?
Right.
You can't compare apples and oranges. You can't swap temperatures and rate constants from two reactions, right? I can't say, well, I'll swap these, but I'm not going to change these. No.
I mean, they have to be in the same order, though.
The same order?
I know that they have to be 2 and 2, but like K1 over K2, then you have to take 1 away from 2 instead of 2 away from 1, right?
Oh, you mean if you swap these in the formula? If you had K2 over K1, it would be 1 over T1 minus 1 over T2?
Yeah.
Yeah, absolutely. Yeah. All right. I mean, think about it. We could put anything we want in there. We could say the ln, they're just letters from the alphabet, right? Ln of A over B is equal to EA over R, 1 over B minus 1 over A. Well, I could swap those letters for anything, you know? I could change this letter to the letter C. So right? So it doesn't matter. If K1, then the T1 has to be here. K1, T2's got to be there. Okay? All right. Well, let's move on and let's try question 17. Question 17, let's see. It says, this is a conceptual question. It says the increase in temperature of reactants causes an increase in the rate of reaction. Hey, we know that because if you crank up the temperature, you have a greater proportion of molecules with a greater kinetic energy, so they're able to surpass the activation energy. Anyhow, it says the best explanation for this behavior is that as temperature increases, what happens? Who could tell me which one of these would be the best answer? And it's not a trick question. Yeah, the answer is A. It's not about the collision frequency. It's about the fraction of collisions with total kinetic energy greater than the activation energy increases, right? If we have more collisions, that doesn't necessarily mean, or that can increase a reaction rate, but it doesn't explain it with respect to temperature. This one explains it with respect to concentration, okay? And we're talking with respect to temperature, right? If you make a plot of kinetic energy versus number of molecules, and this is the Boltzmann curve that we look at. If you have an initial temperature like this, let's say T1, and then you crank up the temperature, you have T2 like this. T2 is greater than T1, and let's say your activation energy is somewhere around here, right? If it's something like this, well, you have a greater number of molecules with enough kinetic energy to surpass the activation energy at T2 than you do at T1. So more molecules with enough kinetic energy to surpass the activation energy. All right, Jamil, does that help? That B kind of describes concentration and not temperature? Okay, good. All right, well, let's move on. And we're getting close to the end now. Question number 18. We covered reaction mechanisms, I think, in the last class, the beginning of last class. It says the following mechanism has been suggested for this reaction. So here's the reaction right here. This is the reaction of interest. And it says here's the mechanism. You got a slow step, you got a fast step, you get another fast step. could anybody identify the molecularity of the rate determining step? Let me ask you a first question. Could anybody tell me which one of these is the rate determining step? No, not a trick.
The slow one.
Absolutely, right? So this one is the, this is the rate determining step, okay? So what is the molecularity of that reaction? Is it bimolecular, unimolecular? Yeah, Noah and David and Stephen, they all say that it's bimolecular. It's A, right? Because, son of a gun. There we go. Because there are what? There are two reactants, right? So two reactants colliding, therefore bimolecular. Bimolecular. You know what? I shouldn't say two reactants colliding. That's not correct. I should say two molecules. Two molecules. Therefore, it's bimolecular. Okay. If any of you decide to study organic chemistry with me next January, which or maybe in the summer or something, I hope all of you will. We'll learn about what are called SN1 and SN2 reactions, and when it's bimolecular, we call that an SN2, or we study types of bimolecular reactions called SN2 reactions, and then unimolecular, we call those SN1. Anyhow, that's neither here nor there. Let's take a look at another question that deals with reaction mechanisms. Hey, I put a couple in here. Maybe I put more than that. Anyhow, number 19, it says the rate law for this reaction is rate is equal to K times NO2 times ozone. Which one of the following mechanisms is consistent with this rate law? I'll give you a second to look at it and see if anybody can figure this one out. Anybody have an idea? Okay, I see that Lauren and Kelton and Jamil, they all put D as their answer. I tend to agree with you, right? Because if we're looking at a mechanism, the slow step, or the rate determining step rather, the slow step, same thing, is going to determine the rate law, right? And if I look at the rate determining step, right, this is our rate determining step, you can see that these are the reactants, and that's an elementary reaction, and its rate would be equal to K times concentration of NO2 times the concentration of ozone, just like that. And that is the same thing as this rate law. And again, the rate determining step is going to dictate the rate law. And so there you have it, my friends. That's the answer, D. Question 20 is meant to be just a pretty quick question. I went over the term molecular with you in lecture. Could anybody tell me which one of these elementary steps would be a termolecular step? These are all different elementary steps. Stephen and Luke and Kelton, you're all in the right vein, right? They all say it's D. This is termolecular because they're all elementary steps. And the rate law for this would be rate is equal to K times A to the power of 2 times B, which is the same thing as rate is equal to K times A times another concentration of A times B, right? I said it's the number of molecules. And in this reaction, we have 3 molecules colliding. Okay, I didn't say it had to be 3 different molecules. I said it had to be 3 molecules. And since there are 3 molecules, right? If we look at the first one is unimolecular, this one is unimolecular, this one's bimolecular, and this one's bimolecular. And so only D is termolecular. Well, let's look at the last question from the practice exam. It says, complete the following statement. A catalyst. I went over catalysts with you. The very last class, we looked at them quickly. Yeah, thanks, Brogan. Exactly. A catalyst just alters the reaction mechanism, doesn't it? We looked at what happens, to our reaction coordinate. We have our, we call this the reaction coordinate. In our book, they call it the extent of reaction, I think. Extent of reaction. Over here, we have energy. If we have our let's call it our normal or our uncatalyzed pathway, and it looks something like this. We'll choose an exothermic reaction, okay, like that. If we have a catalyzed pathway, we're going to have the same energy of our reactants and products, but we change the pathway, right? Something like this, maybe. Okay, fix that up. And yeah, it doesn't matter. There we go. And they're like that. Okay, we don't change the difference in the energy of the reactants or products, but we change the pathway and we lower the activation energy. This would be the catalyzed reaction pathway, and this would be the uncatalyzed reaction pathway. And that, my friends, is the end of the exam, the practice exam 1. Now you've gone through your first entire practice exam in General Chemistry 2. And with all that in mind, what I want to do now is I want to go back into our lecture slides all the way back here. And there was a question. You're going to have to forgive me. It's going to take me a second to find it. But there was a question on this one here. Okay, the method of initial rates. And we didn't do this one, and this one's kind of a long one. And I wanted to give this one a shot. I'll give you a second to look at it. The exam has 21 questions, just like the practice exam. All right, it is 21 questions, just like the practice. Emma, I'm not sure if I understand your question, so maybe you want to email me about that, and I could take a look, or we could discuss exactly what you mean by that. But the reason I wanted to try this problem with you is because one of my students, or a couple of my students, said something kind of interesting that really piqued my interest. I don't know if it was the last class or a couple of classes ago, but it was something that really got me thinking. And what I did is I solved one of these problems, which is just the method of initial rates, but I solved it just using mental math. So just kind of quickly. And a student wrote in the chat, student said, I actually found that easier than when you wrote out the entire, all the rate law and did everything on a calculator. So we're going to solve this problem using mental math. Now, I promise you that none of the mental math in here is mind-boggling. It'll all be calculations you're able to do in your head. If you can make change from $100, you'll be able to do, you'll be able to do this problem in your head. It looks intimidating when you look at this big table of data here, but let's go through it step by step and see if we can figure this problem out. So I kind of run into space here on the side, but it says here, this big reaction, H2SCO3 plus 6I minus plus 4H plus gives you selenium plus 2 I3 minus plus 3 water molecules, was studied at 0 degrees Celsius. Okay. The following results were obtained. Temperature was held constant the whole time, every reaction or every experiment, and it asks us to determine the order of the reaction for each reactant and write out the rate law. Okay, so that's step number 1, is we want to determine the rate law. Now, what could we write down initially? We could say this. We could say the rate is equal to K times the concentration of H2SeO3 to the power of X times I minus to the power of Y times H plus to the power of Z. Okay, we got that much, right? We can go that far. So let's start out by solving for X. Okay, let's start by solving for X. Now, if we want to solve for X, we need to find 2 experiments where the concentration of H2SeO3 changes. And in the same 2 experiments, we've got to have the concentration of the other reactions, or we would like them to stay the same. So if we compare experiments 1 and 2, you see we have exactly that. The concentration of the H2SeO3 changes. It goes from 1 to 2 times 10 to the negative 4. The rate changes. That's neither here nor there, really. But we also see that the concentration of the 2 other reactants remains the same. Now, would I divide R1 over R2, reaction 1 over reaction 2, or would I divide reaction 2 over reaction 1? That's up to you, man. You do what you want. But Mr. Dion, what he always does is I always choose the higher number over the lower number, right? It's easier to divide, mentally. Now this, you don't laugh at me, okay? But it's easier to do 2 divided by 1 than 1 divided by 2. You walk up to the average person on the street and ask them, what's 8 divided by 1? They'll say 8. What's 1 over 8? They'll be like, hold on. I think I hear my mother calling me, right? So I always choose the big one over the little one. What am I trying to say? That in this case, I would choose R2 over R1. You see that R2 is bigger than R1. Look, who can divide 1.66 divided by 0.83 in their head? Can anybody do that? And if you're like, well, what about the exponent, Mr. Dion? Yeah. Right? They cancel. So if I take 1.66 divided by 0.83, what does it equal? What is it?
2.
2, exactly. That's all I was looking for. So that means it's going to be 2 is equal to, what's the change in the concentration of H2SeO3? It's 2 times 10 to the negative 4 divided by 1 times 10 to the negative 4. That means it's 2 to the power of x. X is equal to 1, my friend. There you go. We've solved the first part. Okay? Let's try to solve for y. Okay, so for y, we need 2 experiments where the concentration of the iodide is going to stay the same, but the other ones, did I choose 5 and 6? Let me pick some different ones then. If we choose, let's choose 6 and 4, okay? Because the concentration of the iodide is changing, and these concentrations are not changing, okay? So let's do R6 over R4. If I take 1.68 and then I divide it by 0.21, 1.68 divided by 0.21, I get 8. So rate 6 over rate 4 is equal to 8. 4 divided by 2 is equal to 2 to the power of x. 2 to the power of y. There we go, 2 to the power of y. Who can solve for y in their head?
It's 2.
No, 2 squared is 4.
Oh, it's 3.
Yeah, exactly. 2 cubed, right? 2 times 2 times 2. There we go. Look, we're almost done. Okay, one more. Now let me just delete some of this spinach because I have a lot of crap written on here. There we go. So I'll use a black font for this one. And the last thing we need to do is we need to figure out z. And for z, I'm going to pick 2 experiments. Shoot, I thought I had them all worked out. But we could choose 5 and 1, right? That'll work. So why don't we choose R5 over R1? Let's see here. Yep, R5 over R1, like that, because the concentration of no. I'm trying to figure out H plus. So let's see.
You use 3 and 4.
3 and 4. Thanks a lot. Here we go. Let's do that. 3 and 4. My students are great. So let's take R3 over R4. By the way, if you ever want to rescue me, feel free. Don't be shy. Okay, 3.33 divided by 0.21. So we get that our rate. Look, when you take 3.33 divided by 0.21, you do that in your calculator, you get 15.86. It's close enough to 16, my friend. Close enough. Okay? And then we take 4 over 1. That means it's equal to 4 to the power of z. So z is equal to what? 4 to the power of what gives you 16?
2.
Absolutely. All right. Great. There you go, my friends. That's it. If you want to solve these by mental math, by all means, be my guest. I have no qualms with that at all. If you look at the solutions to this problem that I have posted on Canvas, I believe I solved it the long way. I typed it all out, rate 1 over rate 2, put in the rate constant. You don't have to do that. Okay? You don't have to do that. And again, and I'm repeating myself here, but I'm over 40. I've earned the right to repeat myself like an old man. In our book, they solved several problems using this technique, just the mental math technique. And so we can write out that now our rate is equal to K times H2SeO3 to the power of 1 times I minus to the power of 3 times H plus to the power of 2. I want to ask you guys a question. Could anybody tell me what the overall reaction order of this reaction is?
6.
Absolutely, it's 6th order. If you do H plus with R3 and R5, there's no problem with doing that. So somebody's asking me, what happens, like what would happen if you were to solve for Z using R3 and R5? You could do that, but since the concentration of the iodide is changing, you'd have to plug the numbers in. But since you've already solved for Y, you would just plug that in. But I would say that's more work, right? You don't need to do that, okay? Anyhow, but again, you could do it if you want it, okay? There's more than one way to skin a cat. There's more than one way to solve this problem. But all roads lead to Rome, right? How many other things can I work in here? Anyhow, let's try one more, or the second part, sorry. It says calculate the rate constant. So the reaction that I chose to use is I used experiment 1 when I solved it. You could use any of the experiments. So I chose the top row. I just chose to use all the data in here. And I said that K, son of a gun, K, my rate constant is equal to the rate divided by concentration of H2SeO3 times H plus squared. I kind of reorganized it here. I minus the 3 like that. And then I just plugged in my numbers. So I did it here. I got 0.83 times 10 to the negative 7 moles per liter per second divided by all this spinach. So 1.0 times 10 to the minus 4 molar times 2.0 times 10 to the negative 2 molar squared times 2.0 times 10 to the negative 2 molar cubed. So if you simplify that, kind of running out of space here, you get the K is equal to 0.83 times 10 to the negative 8 moles per liter per second divided by, and the reason I'm doing the whole thing is I just want to show you the units quickly. This is one of the first problems we did in this chapter, right? We practiced units. So you have molar to the power of 6. So if you take molar, molar to the power of 1, subtract molar to the power of 6, well, you end up with 2.6 times 10 to the 5th power molar to the minus 5. So kind of interesting units here. Seconds to the minus 1. And there you have it, my friends. Give me a thumbs up if you're like, I'm digging this mental math for the method of initial rates. All right, good. Who's feeling more confident about the method of initial rates now?
Oh, I did this so much yesterday.
You did what so much?
All this math.
Good. That's great. The best way to master the content in this class, or really the only way, is to practice, 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 right? All right, there's some other problems that we didn't do, and I want to take a quick peek at a couple of those. Where was it? We did that one, 16. I wanted to try 16 with you. I don't know if I have enough room on here to solve the whole thing, but I'll do my damnedest to get it stuffed onto this page. Let's see. All right, it says butadiene, C4H6, reacts with itself to form a dimer with the formula C8H12. The reaction is second order, so that's information they've given us right away. So that means you would use a second order integrated rate law, the half-life for a second order integrated rate law if you need it, so on and so forth. The rate constant is found to be this, 4.0 times 10 to the minus 2 molar to the minus 1 seconds to the minus 1 at a given temperature. The initial concentration is this. What's the molarity of C4H6 after a reaction time of 1.00 hours? So a student asked me earlier, like, how do I know what formula to use? Well, let's try the method of just writing down what the hell we know. First thing we know is that the reaction is second order. Now, if this is the reactant, that means that the rate is going to be equal to the rate constant times the reactant, C4H6, to the power of what? Who can tell me?
2.
Exactly. Okay, nothing more than that. React to the power of 2. Why? Because it's a second order reaction. Okay, so let's scribble that down. Sorry, I'm just organizing my notes here, which are a total gong show. Anyhow, there we go. So we got to the power of 2. What else do we know? We got the rate constant, K, is equal to 4.0 times 10 to the negative 2 molar to the minus 1 seconds to the minus 1. Initial concentration of the butadiene, so we can write down that the initial concentration, C4H6, sorry about that, is equal to 0.0200 molar. And it's asking us, what is the molarity? So they're asking us the concentration of C4H6 is equal to what? When we have a reaction time, T is equal to 1.00 hours. So there we go. We got a rate constant, we got an initial concentration, and we got time. Could anybody tell me what formula I would use to solve for the concentration of my butadiene after 1 hour?
Well, if you look at the handout sheet, then it's probably integrated rate law.
Integrated rate law. Which one would I use?
The second order one.
Exactly. I would just go for the second order integrated rate law. Nothing more than that. We know the second order integrated rate law. I'm going to write it out, and I'm going to substitute in C4H6 instead of A, like is on the handout. But you have 1 over the concentration of C4H6. Subtract 1 over the initial concentration of C4H6 is equal to KT. Looky, looky. We got T, we got K, we got initial concentration. We can solve for this. It's just a matter of rearranging the formula, right? Let's do it. Let's solve for, we can start by solving for 1 over the concentration, I guess. If you want to break it down step by step, we'd say that 1 over C6H, did I say C6 when I meant C4? What the hell? There we go. 1 over C4H6 is equal to KT plus 1 over the initial concentration of C4H6. So that means that C4H6 is going to be equal to KT plus 1 over the initial concentration of C4H6. All of that to the power of minus 1. All right, if you want to write 1 over it, go be my guest, but that means this exact same thing. Now, there's only one caveat. Before I just start going crazy and plugging numbers in this formula, does anybody notice there's one other change that I need to make before I just throw stuff in there? There's something that doesn't jive here. Can anybody tell me what it is?
Hours and seconds.
Son of a gun. Got it. Okay. So what this lady is saying is she's saying, well, look, Mr. Dion, you got a problem, man. You got time in hours, but your rate constant is in seconds. Can you imagine how big of a boo-boo you would make if you set up everything correctly, you plugged in all the numbers, you even did the math, but you didn't convert this into seconds? You'd get the wrong answer. And if you're like, well, that's kind of harsh, well, look up the Mars Climate Orbiter if you don't believe me. Mars Climate Orbiter. Okay, you could look it up on Wikipedia, and you can see how expensive it can be if you miss the units, because that's a $125 million mistake, I think. And it was just because they didn't convert from pounds to newtons, correctly or something. So, and that was by a team of scientists. So you can see how they screwed up a lot worse. So anyhow, in 1 hour, we have 60 minutes. And then in 1 minute, we have 60 seconds. 60 seconds. So hours cancel, minutes cancel. And we get that our T in seconds is equal to 3,600 seconds, like that. Now we have everything. We'll plug all the numbers in here. So let me just make sure I'm not going to confuse anybody. Line here and start plugging some numbers in. So I get the concentration of my C4H6 is equal to 4 times 10 to the negative 2 molar to the minus 1 seconds to the minus 1. Oh, shoot, I'm going to run out of space. 3,600 seconds plus 1 over 0.0200 molar. And I'll put that in brackets here. Sorry, I'm kind of running out of space here. And all of that will be to the power of minus 1. You see that seconds cancel. And we end up with molarity in the end. And when you punch all that spinach into your calculator, I simplified it even more. Sometimes it's good to do that, you know, rather than to try to punch everything in your calculator in one shot. You get 1.4 times 10 to the 2 molar to the minus 1 plus 50 molar to the minus 1, and all of that is to the power of minus 1. And then when you work that out, you get C4H6 is equal to, its concentration is equal to 5.3 times 10 to the negative 3 molar. Comme ça, as we say in French. All right, that's it. Okay, well, I'm going to skip question B because it's kind of in the exact same vein. You use the same formula, except you have the concentration given to you and you're just rearranging to solve for T. Okay, so that's all you're doing in part B, but we haven't talked about half-life in a few days. So let's talk about, so this is A. Let's talk about B, or sorry, C. Let's talk about C. It's asking you to calculate the half-life in seconds of the reaction when the initial concentration is 0.0200 molar. Well, you would look at the first order integrated rate law and the half-life that is derived from that. If you go back in our lecture videos, or if you showed up to every class, which I know you all did, we even derived every stinking, every half-life, right? I remember I did it with you, okay? We did it for a second order, we did it for a first order, and we did it for a zero order. Anyhow, and you should know how to recognize that. So again, it's on your handout, and the formula is the half-life for a second order reaction is equal to 1 over K times the initial concentration of A, just like that. So we have 1 over our K, which is 4.0 times 10 to the negative 2 molar to the minus 1 seconds to the minus 1 multiplied by 0.0200 molar, like that. You can see that these cancel. We end up with our half-life in seconds, and we end up with 1.3 times 10 to the 3 seconds, like that. There we go. Half-life, my brain goes to the game. I'm not sure what that means, but anyhow. All right, we did question 17. There was another one I wanted to do. This one. Yeah, we could try this one here, number 19. I hope you guys are feeling a little more confident as we are wrapping up our practice. I feel like we did a lot of practice problems during lecture. You know, get a lot of extra practice problems at the end of the chapter that you can look at. I've provided the solutions for those. You have the entire solutions manual for the OpenStax textbook. There's a lot of good practice in there. The homework, a lot of practice in there. And the practice exam. So practice, 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 practice. All right. Anyhow, let's take a look at 19, and then we'll probably call it a day. It'll probably take me the rest of the class period to solve this one. It says a certain reaction is the following form. A produces B at a particular temperature. The initial concentration of A is 2.00 times 10 to the minus 2 molar. In concentration versus time measured in minutes, the data was collected for this reaction. In a plot of the ln of A versus time resulted in a straight line with a slope numerical value of negative 2.97 times 10 to the minus 2, right, is measured as the disappearance of A over time. Well, if I get a linear slope when I plot the ln of A versus time, could anybody tell me what the reaction order would be? And it's not a trick. Sorry, I couldn't hear it. It's the ln. Sorry?
I think he said 0.
It's not 0 and it's not second. Okay, it's first order. All right, if we go back here, these are all the equations that you're going to get. A first order integrated rate law plots the ln of A versus time. Okay, look, let's maybe summarize it in a table here. I did this in a lecture, okay? Everybody memorize this, okay? You know, I don't know, memorize it. Sit down after class and go, if I want a linear slope for a zero order reaction, I must plot the concentration of A. If I want a linear slope for a first order reaction, I must plot the ln of A. If I want a linear slope for a second order reaction, I would plot the 1 over the concentration of A. You got to memorize that, I guess, okay? Memorize, okay? All right, there we go. So when we plot for a first order reaction, when you plot the ln of A over time, or ln of A versus time, you end up with a negative slope, right? That is equal to negative K, and the y-intercept is equal to the ln of the initial concentration. Look, you guys, stop and think carefully. You can plot whatever the hell you want. You can plot, 23.2 to the power of -4 multiplied by the concentration. It doesn't matter what you're plotting. What I'm telling you is this. Here's the answer. I'm giving you the answer. If you plot concentration of A versus time and you get a straight line, it's zero order. If you plot this other shit, it's not going to be straight. You're going to get a curve, sure, but curved slopes are pretty hard to interpret, my friend. A linear slope is a much easier thing for a person to interpret. If you plot the ln of A and you get a straight line, that means it's first order. Yeah, you can plot this other crap. You can plot both of those. You can plot whatever you want, man, but you're not going to get a straight line. And finally, if you plot the reciprocal of the concentration of A versus time, and you get a straight line, it's second order. Yes, you can plot this crap. No problem. Be my guest. But you're going to get a curve, and curves are not very helpful. Okay? Yes, I know that you've all studied, calculus and I've seen curve plots, Mr. Dion, so that I was dreaming about them. Okay, great. But that's not what we're talking about in this class. Let me look. I'm not frustrated. I just want everybody to ace this, okay? Where's a question that I asked? This question right here, okay? I'll delete everything that's here, okay? Let me delete this. Delete. Look, let's read question 13 from the practice exam. The graphs below all refer to the same reaction. You can plot whatever you want. 1 over A, ln of A versus time. You can plot any damn thing you well please. But the only plot that's going to really have any meaning to you, that's really going to be helpful for you to determine K, is the one that gives you a linear slope, because it gives you negative K. This shit, I got to stop doing that. Anyhow, this one and this one, that didn't help you with K. Okay? No pun intended. All right, so we're looking for a linear plot. So when you see concentration of A versus T, we go back here. What was our mantra? Where the hell are my slides? Oh, shoot, I'll never find it now. But anyhow, you remember what I said when we were meditating there a second ago? Jeepers. I'm going to watch my mouth. I don't even know where it was now. Was it down here that I talked more about the plots with you guys? Yeah, I think it was here. Yeah, right here. Okay, so if you plot concentration versus time and you get a straight line, it's zero order. Anyhow, I think I've eaten up all the time. Give me a thumbs up if that helps you. Okay, that's a really big concept. 3 reactions that you need to know. 0, first, and second order integrated rate laws. If you're wondering, like, hey, Mr. Dion, is there a third order integrated rate law? Of course. Is there a bimolecular integrated rate law, Mr. Dion? Absolutely there are. Absolutely. But you don't want to learn that right now, okay? That is beyond the scope of our class. That's something totally different. And that would get a lot more complicated. Think about it. These integrated rate laws that we're doing, they're all for the same reaction. They're all just A gives me products. Once you get A plus B gives you products, oh, then you open Pandora's box, my friends. It gets a lot more complicated. All right. There we go. Okay. There we go. So